Hello my friends and welcome back to the Today Machine channel. Flow form wheels are produced using a process known as flow forming, which combines elements of both casting and forging. At this stage, engineers adjust the design to meet the specific requirements of the vehicle and the intended applications. To ensure the design strength, finite element analysis (FEA) is employed. The production process starts with a bar of this aluminum alloy, which is melted in a furnace at approximately 1,400 degrees Fahrenheit, 760 degrees Celsius. The molten aluminum is filtered, degassed, and inspected before being poured into a steel mold, which forms the wheel's face. Depending on the mold size, between 50 to 100 pounds of molten aluminum, now at over 1,300 degrees Fahrenheit, 704 degrees Celsius, are poured into the mold. Once the aluminum solidifies, the casting is removed from the mold and quenched in water at around 120 degrees Fahrenheit, 49 degrees Celsius. Any excess material, known as flashings, is removed, and the wheel's dimensions are verified to ensure it meets the correct specifications. At this point, some of the wheel's spoke design can be observed, but one key characteristic of flow-form castings is the short rim barrel skirt, which has not yet been fully molded into its final shape. The flow forming process begins with this skirt of material. The casting is loaded onto a conveyor and passed through a preheating oven, preparing it for the next stage. The mandrel, a tool shaped like the rim's profile, is pre-sprayed with a release agent to facilitate the wheel's removal after forming. The heated casting is then placed onto the mandrel, where rollers slowly press the aluminum skirt into the final rim barrel shape, stretching and squeezing the material in multiple passes. This process refines the metal's crystalline structure, enhancing the wheel's strength and its ability to absorb impacts more effectively than fully cast wheels. Once the rim barrel is formed, the wheels are again quenched to lock in their mechanical properties and minimize any distortion. The next stage involves heat treatment, which further strengthens the aluminum by refining its structure. The castings are heated and then quickly quenched, solidifying the correct hardness and durability for the wheel. With the flow forming and heat treatment stages complete, the wheels undergo a series of rigorous quality control tests. X-rays are used to inspect the wheels for any internal defects, such as voids or cracks, that are not visible to the naked eye but could compromise the wheel's structural integrity. The visible ridges on the wheel's barrel at this stage are the result of the flow forming process and demonstrate the controlled stretching of the aluminum. After this, the wheel's final rim profile is shaped through a lathing process, which removes excess material and achieves the precise geometry intended by the designers. Detailed machining follows, creating the lug holes, hub bore, and valve stem hole. Before the wheels proceed to finishing, they undergo a balance and run-out check to ensure they are perfectly round and balanced. This step verifies that the wheels will meet performance and safety standards. The wheels are also subjected to a leak test, which simulates the pressure exerted on the wheel when a tire is mounted. This ensures the wheel can maintain proper tire pressure under load, which is critical for vehicle safety. Once the wheels pass these quality control tests, they are cleaned thoroughly to remove any debris from the manufacturing and machining processes. After cleaning, the wheels are moved to the painting line, where a powder coat finish is applied. HRE's standard black powder coat, known as tarmac, is electrostatically applied, with the powder being charged to adhere to the wheel's surface. The wheel is then heated, melting the powder into a hard, durable coating. A liquid clear coat is added to give the wheel a satin sheen and protect the underlying paint. Throughout this process, the wheels are spun to ensure an even application of the coating across all surfaces. In addition to the standard tarmac finish, HRE offers a finish called liquid metal, which is achieved using a hand-sprayed fading technique. A base black coat is first applied, followed by a liquid silver spray over the wheel's face, creating the dynamic, multi-dimensional look of the liquid metal finish. HRE Flowform wheels are all designed to meet strict German TÜV standards and undergo rigorous physical testing to ensure they meet these high-performance criteria. One of these tests is the radial fatigue test, which simulates long-distance driving under load to assess the wheel's durability and resistance to cracking. Another test, the cornering test, replicates the forces experienced during high-performance cornering, while the impact test simulates real-world scenarios like potholes or other abrupt impacts. In this test, the wheel is designed to deform but not lose air, allowing the vehicle to come to a stop safely without suffering tire pressure loss. After all tests are completed, a red dye penetrant and a white topcoat are applied to the wheel, making any cracks or defects visible during the final inspection. The wheel undergoes several more quality control steps, including checks for size, offset, lug pattern, and center bore accuracy. The visual appearance of the wheel's finish is also inspected from both the front and back to ensure it meets HRE's high standards. The 3-roll variable axis plate rolling machine is designed to bend thick plates, such as the 130 mm, 5 inches plate, with a powerful top roll exerting 4,000 tons of bending force. It has a top roll length of 4,250 mm and a diameter of 1,260 mm, enabling precise control over large, heavy plates. This machine works by positioning the plate between the top and lower rolls, which move to apply pressure and roll the plate into the desired cylindrical shape. The tilting of the rolls enables the machine to bend conical shapes as well. The 3-roll system enhances flexibility and accuracy, utilizing hydraulic and mechanical symmetry to ensure even load distribution. Its servotronic system guarantees roll parallelism for consistent, high-quality bending results. The machine can complete the bending process quickly, producing minimal flat ends and maximizing productivity. The ball-making machine for ball valves is an automatic transfer-type machine designed for efficient, high-precision production of valve balls. Its process begins with auto-loading, where a hoist lifts raw material balls, called blanks, onto the machine. From there, a linear feeder automatically aligns and transports the blanks into the first station for processing. At the first station, a hole is drilled into the blank, creating an opening needed for the valve's internal function. The blank then moves to the second station, where milling operations are performed to shape specific parts of the valve, such as flat surfaces or other design-specific features. Next, the blank is transferred to the third station, where slotting takes place. This process involves cutting a groove or slot, which could serve as a guide for positioning or function within the valve system. Finally, the blank is processed at the fourth station, where mirror turning and chamfering occur. In this stage, the blank is machined to ball. Mirror turning smooths the surface to a fine, reflective finish, ensuring the ball can rotate smoothly within the valve. Chamfering adds beveled edges to eliminate sharp corners, enhancing functionality and safety. After completing the final operation, the machine performs auto-unloading, seamlessly removing the finished valve ball from the production line for further inspection or packaging. The valve manufacturing industry in China is a critical component of the country's broader industrial sector, serving industries such as oil and gas, power generation, water treatment, chemicals, and pharmaceuticals. China has established itself as one of the world's largest valve producers, contributing significantly to both domestic consumption and export markets. The Chinese valve market is projected to exceed 20 billion United States dollars by 2025, driven by infrastructure development, energy demand, and increased urbanization. China's valve production capacity is immense, with over 3,000 valve manufacturers spread across key industrial regions. Zhejiang Province, particularly Wenzhou, is known as the valve capital of China, hosting around 70% of the country's valve production. This region is home to leading companies which are renowned for their wide range of valve types, including ball valves, gate valves, butterfly valves, and control valves. One of China's top valve manufacturers reported a revenue of approximately 590 million United States dollars in 2022, highlighting the growth potential in this sector. China's valve exports have also surged, with valves being shipped to more than 100 countries. In 2022, China exported over 8 billion United States dollars worth of valves, with major markets including the United States, Europe, Southeast Asia, and the Middle East. Technological advancements in valve manufacturing have played a significant role in China's rise as a global player. Companies have invested heavily in automation, CNC machining, and digitalization to enhance production efficiency and ensure compliance with international quality standards like ISO 9001, CE, and API 6D certifications. China's focus on clean energy and environmental regulations has further spurred demand for advanced valve technologies, including high temperature, high pressure, and corrosion-resistant valves. However, challenges remain. The industry faces rising raw material costs, competition from low-cost producers, and increasing environmental regulations. Nevertheless, China's valve manufacturing industry is poised to maintain its growth trajectory, supported by strong domestic demand and its expanding presence in global markets. Forging is a crucial process in manufacturing, particularly in industries like oil field drilling. It involves shaping metal through controlled deformation, typically using compressive forces like hammering or pressing. Forging bodies for oil field drilling tools, such as drill bits, stabilizers, and reamers, requires precise material selection and process control to meet stringent industry standards. These forged tools are manufactured from high-quality materials and non-magnetic alloys, which are vital for the durability and performance of oilfield equipment. Forged components are widely preferred for their superior mechanical properties, including increased strength and toughness compared to castings. Free forging, a flexible method, is often used for producing small batches of varied parts, offering advantages in material utilization and customization. This method is suitable for producing parts like shafts, rings, and spindles, where the grain structure remains uninterrupted, contributing to higher fatigue resistance and better performance under stress. Forging also enhances the internal structure of metals, eliminating defects like porosity and improving overall mechanical properties. Heat treatment and further machining processes can be applied to tailor the mechanical properties of the forged components, ensuring they meet the exact requirements for oilfield drilling and other demanding applications. Over the years, this facility has supplied these high-quality forged tools to more than 20 countries and regions. The large bar mill at Hyundai Steel's Dongjin plant is a state-of-the-art facility, producing up to 1 million tons of carbon and alloy steel each year, mainly for automotive applications. The process begins with the charging of blooms into a reheating furnace that has a capacity of 200 tons per hour. The blooms are heated to the required temperature and then descaled using a high-pressure water primary descaler. After descaling, the heated blooms enter the breakdown mill, which consists of a two-high reversing housing type mill with a maximum roll diameter of 1,200 millimeters and a barrel length of 2,600 millimeters. The mill handles both hot and cold charging and processes large blooms of 390 by 530 millimeters in size and 3.5 to 8 meters in length. The blooms are processed into intermediate square products, and hydraulic shears are used for bar end cropping with a cutting capacity of 1,000 tons. The intermediate square products are then rotated at a 45 degrees angle before proceeding to the continuous mill. Before entering the continuous mill, the intermediate products undergo another round of descaling. The continuous mill consists of 6 stands for finishing and sizing, with Red Ring Series 5 stands for the finishing process and CGA stands for the sizing process. The stands allow for precise shaping of the bars, with working roll centerline distances of up to 1,030 millimeters for the finishing stands and 870 millimeters for the sizing stands, both featuring a barrel length of 1,200 millimeters. The mill uses a quick stand change system to minimize downtime between product changes. A ProScan laser profile gauge ensures dimensional accuracy during this stage. Once the bars pass through the finishing and sizing stages, they move along the exit roller table and into layer forming systems. The plant is fully automated, handling the final stages of the process, including cutting, bundling, and marking the bars. Cut-off machines equipped with metallic disc saws, 1,800 millimeters in diameter, are used to crop the head and divide the bars into commercial lengths. The bars are then cooled on turnover cooling beds, where they are continuously rotated to ensure uniform cooling. The large bar mill at Hyundai Steel produces round bars in sizes ranging from 80 millimeters to 350 millimeters in diameter. After the initial reheating and descaling processes, blooms are reduced to round bars using the breakdown mill and the continuous finishing and sizing stands. A ProScan laser profile gauge ensures the bars meet precise dimensional standards. After exiting the mill, the round bars are cut to commercial lengths using flying dividing shears with a 300-ton cutting capacity. The bars are cooled, bundled, and prepared for shipment, making them suitable for use in various automotive and industrial applications. A weighing system ensures accurate final product weights. The facility also includes a bundle binding station for preparing the finished products for transport. The closed die forging process, also known as impression die forging, is a manufacturing technique used to shape metal under high pressure, producing highly precise and durable components. The process begins with cutting the raw material to the required size and weight. The material is selected based on the required mechanical properties and performance of the final product. The next step involves heating the dies, which are the pre-shaped molds into which the material is pressed. Preheating the dies prevents thermal shock and ensures uniform material flow during forging. The temperature of the dies is carefully controlled, typically ranging from 1000 degrees Celsius to 1250 degrees Celsius, depending on the type of material and the complexity of the part. Once the material and dies are prepared, the preheated material is placed into the lower die. The upper die is then pressed onto the material using a forging press or hammer, forcing the material to flow into the cavities of the dies. The immense pressure applied ensures that the material fills the entire die cavity, producing a component with high dimensional accuracy and excellent mechanical properties. Excess material, called flash, is squeezed out around the edges, which is later trimmed off. After forging, the component undergoes heat treatment to enhance its mechanical properties, such as strength, toughness, and resistance to wear. This process involves heating the part to a specific temperature and then cooling it at a controlled rate, often through quenching in water or oil. Once heat treatment is completed, hardness testing is performed to verify that the part meets the required specifications for its intended application. This step ensures the component has the necessary durability and strength. The final step involves shot blasting, where small steel pellets are blasted at the forged part to clean off surface impurities, scale, and residues from the forging process. This process also gives the component a smooth, polished finish, improving its appearance and surface integrity. Forging technology plays a critical role in modern manufacturing by producing high-strength, durable components that are essential for industries such as automotive, aerospace, defense, and heavy machinery. The process involves shaping metal through compressive forces, often using hammers, presses, or dies, at elevated or room temperatures. Forging improves the mechanical properties of materials by refining the grain structure, enhancing toughness, fatigue resistance, and tensile strength, which is vital for safety-critical applications like crankshafts, aircraft landing gear, and heavy-duty axles. Modern forging techniques include open die, closed die, and impression die forging, each suited to different applications and material types. Closed die forging, for example, is widely used in the automotive industry to produce high-volume, precision parts such as gears and shafts. On the other hand, open die forging is ideal for creating large, custom components such as turbine shafts and large flanges. Advanced forging technologies, such as isothermal forging and radial axial ring rolling, are utilized for producing complex shapes with minimal material waste and superior dimensional accuracy. Technological advancements like simulation software have transformed forging by enabling manufacturers to predict material flow, stress distribution, and final part properties. This allows for optimization of the forging process, reducing material costs and minimizing defects. Furthermore, forging processes are now integrated with automated systems, enabling high production rates and consistent quality. Forging technology is also highly compatible with modern materials like titanium and nickel-based superalloys, which are essential for high-temperature applications in aerospace and energy industries. As a result, forging remains indispensable in the manufacturing of components that require superior strength, durability, and performance under extreme conditions. CNC machining technology revolutionizes manufacturing by enabling precise, automated cutting, milling, and turning of parts. Modern CNC machines can achieve tolerances as tight as plus or minus 0.001 millimeters, ensuring high precision in mass production. This technology enhances productivity by reducing manual labor and eliminating human error, offering high repeatability and consistency. In terms of speed, CNC machines can operate continuously, reaching spindle speeds of over 15,000 RPM, which translates to faster production cycles. This efficiency reduces lead times and costs, making CNC machining an integral part of industries that require high accuracy, such as aerospace, medical device manufacturing, and automotive production. The production of drill pipes begins with the use of high-quality raw materials, typically premium alloy steel, which ensures the durability and strength required for demanding drilling operations. The steel is processed according to international standards, such as API Spec 5DP. The first step in production involves forging, where the alloy steel is heated and shaped into long cylindrical rods that will form the body of the drill pipe. Once the pipes are forged, they undergo a heat treatment process, which enhances their toughness and resistance to wear and tear. This is a crucial step to ensure that the pipes can withstand the high pressure and extreme conditions of drilling. After heat treatment, the pipes are machined to apply precision threading to both ends. These threads are often fitted with advanced double shoulder connections, which provide increased torque capacity and stability during use. To protect the drill pipes from corrosion and wear, they are coated with various treatments. The heavy lift vessel MV Lone underwent a significant upgrade from a DP1, Dynamic Positioning 1, system to a DP2, Dynamic Positioning 2, system at the Norderwerft shipyard in Hamburg, Germany. This transformation was carried out to enhance the vessel's capabilities for more complex offshore projects, especially in the gas, oil, and wind energy sectors. The MV Lone, known for its high crane capacity and impressive speed, was prepared for more demanding offshore operations that require precise positioning and greater operational redundancy. Installation of additional bow thruster and retractable azimuths. The upgrade started with the installation of a second bow thruster. This additional 1,200 kilowatts bow thruster was crucial to improving the vessel's maneuverability, particularly in challenging offshore environments. The bow thruster, located at the vessel's front, enables precise lateral movements and contributes to maintaining the vessel's position during dynamic positioning operations. In addition to the bow thruster, two retractable azimuth thrusters were installed. These azimuth thrusters, also rated at 1,200 kilowatts each, are located both at the bow and aft, rear, of the ship. Their retractable nature allows the vessel to operate efficiently by deploying them when needed for enhanced maneuverability and retracting them during transit to reduce drag and improve fuel efficiency. The azimuth thrusters are capable of rotating 360 degrees, which further contributes to the vessel's precise positioning, especially during offshore operations. The installation of three 1,600 kilowatts auxiliary engines was another vital component of the upgrade. These engines ensure that the vessel has a reliable and redundant power supply, which is essential for the DP2 system to function effectively. The DP2 system requires the power to be split across multiple sources so that the vessel can maintain its position even in the event of a single point of failure, ensuring safety and operational continuity. Bridge control and engine room modifications. The upgrade also included significant electrical work and the installation of new control panels on the bridge. The new dynamic positioning system required an overhaul of the vessel's control systems to integrate the additional thrusters and auxiliary engines. This also involved substantial electrical modifications in the engine control room to ensure that the new power distribution system could be managed effectively. These upgrades were designed to ensure smooth operation of the vessel's new capabilities and allow the crew to monitor and control the vessel's position with greater precision. To optimize the functionality of its high-capacity cranes, particularly during offshore lifting operations, the MV Lone was equipped with a motion monitoring system. This system enhances the vessel's stability and safety when performing lifts at sea, which is often subject to unpredictable environmental conditions. The system monitors the vessel's movement in real time, allowing for adjustments that help maintain crane operation safety and efficiency, a critical factor in offshore construction and heavy lifting projects. Once the upgrade was completed, the MV Lone departed from Norderwerft and headed for sea trials in the Baltic Sea. These trials were essential for testing and calibrating the new DP2 system, ensuring that it performed according to specifications. The DP2 system is designed to keep the vessel at a designated position with greater precision and reliability compared to DP1, making it ideal for tasks that require stability in rough seas or in close proximity to offshore structures. During the trials, the performance of the additional bow thruster, azimuth thrusters, and auxiliary engines were thoroughly tested, as well as the integration of the motion monitoring system. The WH-10 CNC machine is designed for precise and efficient machining of valves, with capabilities tailored to handle complex geometries and large workpieces. With travel ranges of X equals 1,250 millimeters, Y equals 1,100 millimeters, and Z equals 940 millimeters, the machine offers ample space for maneuvering and machining various parts of a valve. The process begins by securing the valve body or workpiece onto the machine's rotary table, which measures 1,000 by 1,120 millimeters and supports up to 3,000 kilograms of weight. The table's rotation ensures that different sides of the valve can be accessed without needing to reposition it, allowing for one clamping, machining, which enhances precision and reduces setup time. The machine spindle can reach speeds up to 2,500 revolutions per minute, providing sufficient power and flexibility to handle various materials, including metal alloys typically used in valve manufacturing. With the integration of a probe measurement system, tool positioning and workpiece dimensions are checked for high accuracy before and during machining. Specialized tools are used for different machining tasks. For instance, a chamfer tool with a diameter of 0.32 mm and a 45 degrees angle is used to create chamfered edges on the valve's ports or seating surfaces. A grooving tool with a 4 mm diameter is employed to cut grooves or threads, essential for sealing or connecting mechanisms within the valve. A tool with a 24 mm diameter is used for general cutting or drilling. The machine's control system allows for precise programming of the machining operations, which can include milling, drilling, and grooving. All operations are performed with high accuracy and speed, thanks to the CNC's ability to execute complex tool paths while maintaining tight tolerances, ensuring a high-quality final product.